I want to introduce today's topic by starting with the big picture. Richard Smalley, Nobel laureate in chemistry in 1996, listed the top 10 challenges that humanity will face in the next 50 years, in the order of importance. In this list, we see water, food, environment. But what is the leading topic or concern that the 21st century will face? Well, if you guessed it right, it is energy. Rapid depletion of our fossil fuels and increasingly worsened environmental pollution caused by fossil fuel consumption has caused a high demand to make energy efficient technology and to seek renewable and clean energy sources. As a result, the field of energy storage has received considerable worldwide concern and has become an area of increasing research interest. So, why should we care? Popularization of portable electronics and electric vehicles worldwide stimulates the development of energy storage devices such as batteries and supercapacitors towards high power and energy densities. The performance of these electronics depends upon the advancement of materials used in these devices. Moreover, energy storage materials play a key role in efficient, clean, and versatile use of energy and are crucial for the exploitation of renewable energy. What is an electrochemical energy storage device? And how does a typical lithium ion battery work? Electrochemical energy storage or release is accomplished by electron and ion charge and discharge. Batteries are an example of a typical electrochemical energy storage device which stores electricity by electrochemical redox reactions. An electrochemical energy storage device is composed of an anode, a cathode, a separator, and an electrolyte. During discharge, when you're using your cell phone's battery, for example, electrochemical reactions occur at the electrodes, causing electrons to flow through an external circuit from anode to cathode, as being shown in the animation. During charge, when you're replenishing your battery life, you can reverse the external voltage, driving the electrons in the opposite direction. But what are the electrodes made of? As mentioned in the previous slide, lithium-ion batteries are made of an anode and a cathode. The anode that is most commonly used is graphite. Graphite particles are mixed with polymeric binder and a conductive additive and casted onto the current collector. Similarly is done with the cathode. But instead of graphite, we have lithium-rich material. This will be the focus of the rest of the talk. Basically, there are two kinds of cathode materials for lithium-ion batteries. The first contains layered compounds with an anionic, closely packed lattice in which alternate layers between the anion sheets are occupied by redox active transition metal, and the Li ions can intercalate into the empty remaining layers. Examples of these structures include lithium titanium disulfide and lithium cobalt oxide. These materials are compact, allowing for higher specific volumetric density. The materials in the second group have more open structures, including many vanadium oxide, the tunnel compounds of manganese dioxides, and transition metal phosphate. Lithium rich layered oxide, LLOs, which fall into the latter category but are pre-intercalated with lithium to achieve higher discharge capacities. The structure of LLOs is described by researchers either as a solid solution or a nanocomposite of Li2MnO3 and LiMO2, where M is a collection of metals, mostly manganese, nickel, cobalt. The different base group of Li2MO3, which is rhombohedral, versus LiMO2, which is monoclinic, arises from the ordering between the lithium and manganese ions in the transition metal layer of the structure. Both LiMO2 and Li2MnO3 have cubic close-packed oxygen array in which all the octahedral sites are filled by alternating layers of lithium and transition metal. Due to the similarity of these phases, the local structure is difficult to reveal. Characterization techniques include high resolution TEM, high angle annular dark field scanning TEM, and electron energy loss spectroscopy.
LIBs are the most important and widely used rechargeable batteries because they operate with high reliability. Layered rich lithium-rich layered oxides are no exception, with the primary advantage of materials having a higher discharge capacity between 200 and 220 milliamps per hour gram and energy density, as they represent a significant improvement over most common commercial LIB cathodes, such as lithium cobalt oxide and lithium manganese 2 oxide 4. Another benefit of these layered oxides is their reduction in cost due to their lower cobalt content, and they're much safer and environmentally friendly. The high discharge capacity of LLOs is derived from its unique first charge-discharge cycle. The initial charge cycle consists of two regions. The first region, which is below 4.4 volts, demonstrates where lithium ions are extracted due to the oxidation of transition metal ions to the 4 plus state. Capacity from this region varies based on the composition of the material and the charge of the current. The second region is the oxygen loss plateau that occurs above 4.4 volts. In this regime, lithium is removed alongside oxygen. Oxide ions are oxidized and lost as O2 gas, but LLOs can be thought of as losing Li2O. During this initial discharge, transition metal ions that are oxidized during sloping regions are reduced back to their initial states. Because of the loss of oxygen ions during this charge, another ion must be reduced. This is believed to occur in conjunction with other mechanisms such as reversible oxygen reduction, side reactions with electrolyte, and or proton exchange, which all add to the capacity. This allows LLOs to reach a capacity up to 300 milliamps per hour per gram. The mechanism recently, however, Delmos et al. Proposed a more complicated mechanism of irreversible oxide ion oxidation and subsequent oxygen loss at the surface of the particles, coupled with reversible oxide from oxidation in the bulk. They used electrochemical measurements, neutron diffraction, chemical analysis, Raman spectroscopy, HAADF, STEM to reach this conclusion by showing oxygen gas as is evolved at the surface. TM ions migrate from the surface to the bulk in a densification process, but the bulk structure does not undergo any significant structural change.
We now come to the challenges that LLOs face. LLOs suffer from voltage decay. Oper- uh, Operating voltage significantly decreases during cycling, causes reduced energy density and difficulty in determining the state of charge of battery cells. They also suffer from low rate capability. The insulating nature of the Mn4 plus ion in the lithium manganese oxide component, a large charge transfer resistance at the interface between the particle and the electrolyte, a thick SEI layer that forms during cycling, poor delithiation kinetics, and the often large particles of LLO synthesized by researchers lead to poor read capability. First cycle irreversible capacity loss, which is also referred to as low first cycle Coulombic efficiency, where values are less than 80%. The first discharge cycle has a large IRC. During the first cycle, not all of the Li ions extracted during the first charge can be inserted back into the structure, causing the high IRC. These excess Li ions are then free to react with the products of the electrolyte decomposition to form a thicker SEI layer. Finally, low volumetric energy density, caused by a combination of voltage decay that insinuates the gradual structural transformation of the LLO material to a spinel-like phase. Capacity fade that leads to the TM dissolution and structural transformation to the spinel-like phase, and often small particle size, which has higher surface area, causes an increased reactivity with electrolyte, a thicker ACI layer, and increased oxygen loss.
Here is a list of our sources used for making this video. Thank you for your attention. Do you have any questions?